A second possibility, which is due to Elsner, is to encode hypernym relationships. So that means, for those of us that didn't know what it means, which I didn't until recently, more specific and less specific words. So for instance, dog is more specific than mammal. Mammal is a sort of more general word than dog. And the idea again is to use density operators to encode that type of information. So typically when we say this, we're thinking about working in CPM of Hill for real Hilbert spaces. But we might want to look at other models, and REL is the sort of natural go-to thing. That's the place everyone looks immediately after Hill. So we'd be looking at models of these things in REL, which make good toy models because they're quite small and discrete and whatever. Okay, so in a recent paper by various authors, not including me, they looked at a linguistics application. They worked in Hilbert spaces, but then as a toy model, they considered CPM of REL, and they looked at the Booleans because they were looking at sort of true-false sentences. So the way they modelled the Booleans was to take a two-element set of truth values, a sort of most probably natural thing that you could do. And in REL, this set of Booleans has four states. So basically states are subsets. So we could think of this as sort of overdetermined, precisely true, precisely false, and underdetermined, if we want to look at it that way. So then the next sort of step in their paper is that they look at the same object in CPM REL, and then we find out that this set bool has 5 states in CPM REL, which, well, I was sort of slightly surprised at this point. Why 5 is kind of the question that immediately leapt to mind, and could I have anticipated that? We kind of expect there's going to be at least 4 because we've got this canonical functor that lets us map up the pure states. We've got 4 pure states. It seems surprising that if you think of CPM REL as mixing, that you maybe only get 1 mixed state here, and it maybe seems a little bit odd. So that's kind of the starting point for looking at this type of thing. Okay, so then the question is, well, obvious place to start. What are the states exactly in CPM REL? And Peter Salinger sorted this out for us as well in an example in his paper. So the states basically correspond to the positive morphisms in REL, which in turn correspond to relations of this form. So they're symmetric, and they have this funny second characteristic, which basically says if you're related to anything, then you're related to yourself. That's probably the easiest way to remember it. And then, as I was trying to understand where 5 had come from, and generally what goes on with mixing in this CPM REL setting, I asked myself the sort of easiest question I didn't know the answer to, which was basically, can we count these guys? So I hacked myself out a little Haskell program and decided to count them in sort of brute force manner. So just for comparison, I've got the states in REL, but it's obvious what the numbers are going to be there. And we get this pattern here where we effectively get no mixed stuff for the empty set, which is maybe not surprising. For the one element set, again, no mixed stuff. That's probably not surprising. Then we get 5 here, which, I don't know, I kind of thought that seemed low, that there was only one way of mixing 4 different things together. And then the numbers follow some funny pattern that was at least unfamiliar to me when I started. And my Haskell skills aren't as good as they should be, so we don't know anything about 6 and so on from my programming skills, unfortunately. So, given that limitation on my programming skills, I sort of have to go back and do some proper work. So, we then look at these relations that were described a couple of slides back, and we can actually, for each one of those relations, we can construct a particular graph. So basically, we take as vertices elements that are related to themselves by the relation, and we take as edges pairs of things which are related to each other. And yeah, an aside, these things are simple graphs, but with a slight proviso that instead of not having self-loops, I insist on self-loops. So they're basically bijective correspondence with them, but it's just more convenient to have that I always have these self-loops. So in particular here, this could be AA, for instance, so that we have self-loops everywhere. Okay, so just some simple examples. So if we just take a relation that just relates A to A and B to B, then the graph we get is just 2 isolated vertices. And when I draw these things, inconsistent with the way when I actually formalize them, I won't draw the self-loops like you would do in category theory. The self-loops just get distracted. But they are sort of there lurking behind the scenes. So the second example, we take the maximal relation on AB, and we get this bone thing, as Pavel described this type of picture earlier in the week. So basically it's the complete graph on AB, so let's just do a couple of examples. Okay, so it turns out after a little bit of work that these graphs are actually in bijective correspondence with these relations that we saw earlier. And that means that we can answer this counting question. So this formula here, which I won't expand on, it basically says if you tot up all the subsets of the set that you're interested in, and then take all the graphs that you can build up of the appropriate type on them, and then add them all up, that basically gives you the number of states that you're interested in. Okay, so we then go on to have a look at what goes on when we take this canonical functor and sort of look at where we end up graphs-wise. So if we take the pure state and map it in, this is a particular example, we get a complete graph x, y, z here. And these two guys aren't in the image of this canonical functor, and so these guys are not pure states or mixed states, if you want to say that. And yeah, it seems to be the pattern then that the pure states are complete graphs or cliques, depending on how you want to look at this thing, and the mixed states are the ones where there are edges missing. And that is true. I'll hopefully get back to that by the end of time. Okay, so as we've characterized the state, we can piggyback that to characterize the morphisms as well, because we've got this map state duality. The morphisms in the categories that we're interested in bijectively correspond to states of this form, but with a star here, because I should have put dual here, that's a typo. So we can consider morphisms A, B to be graphs on subsets of the Cartesian product of the domain and codomain that we're interested in. Okay, so this is a bit of a wordy slide, but basically we can define the category G. So kind of the point of this slide is just to say what G is later. So the objects are sets, and the morphisms are these graphs that we mentioned on the previous slide. And then we have to say what the identities are. So the identity is going to be the complete graph on the diagonal of the set that you're interested in. And the composition, I've written it down, not formally, but sort of in words at least down here. But the basic idea is that if you're taking something from A to B and something from B to C, then you can glue things together where the B parts match up. So if you want the details, you can see it in the paper formally, or you can look at this example. So we have an AB morphism here, so it's a nice simple thing. It's just got one edge, and these things are now labelled by pairs, as I mentioned earlier. And then this is a BC thing, so we've got this set of things here. And immediately we can see this thing is labelled with B double prime. I'm assuming all these things aren't labelled up but distinct. And there's no mention of B double prime here, so there's no way of gluing these things together compatibly. So this guy's going to kind of disappear, so that's what we don't see. It's down here. And similarly, when we glue together edges, we see that the BB prime bit here is compatible with the diagonal here, so we get a diagonal down here. And then we also get this edge here, and that comes from the not drawn self loop here. So that's the self loops do matter for the definition of this composition. Okay, so, well, doing a little bit of work, this turns out to give you a well-defined category. The details are obviously not the sort of thing we want to go through now. And it turns out, in fact, that we have an isomorphism of categories between CPM rel and this category of graphs. Right, I've got the accelerometer up, so I'm now going to start accelerating. So, given this isomorphism, we know that CPM rel is a dagger compact monoidal category, and we also know that we can take unions of morphisms. And the question is, can we describe this structure in terms of graphs? Okay, so we have the canonical functor. We can sort of take that to be a thing that takes things straight into graphs just by composing with the isomorphism we've got. And it turns out basically if you take a relation, consider it as a subset of AB of the domain and codomain, and then take a complete graph on that, that's how you lift morphisms using this functor. So in particular, as I mentioned earlier, the pure states are the complete graphs. That's where that comes from. Okay, the dagger is very easy. You leave the graph as it is, and you flip the labels around. So you see these ABs are getting flipped to BA. So that's a nice, easy operation to do graph Okay, tensor products. The basic idea here is if we've got two morphisms we want to tensor together, so they'll be in terms of pairs, then we basically glue these things together. So if we've got ABCD, we glue that together as a vertex ABCD. And if we've got an edge on the AB side and we've got an edge on the BC side, then in that case we get an edge between the other guys. So this is an example. I won't belabor this as I'm already on the accelerometer. So we take these two simple graphs here and we tensor those guys up. And we get this thing, which isn't a complete graph, although there's lots of arrows around. There's some extra edges that aren't in here, for instance, this guy here, so we don't get complete graphs. Okay, so we also got some order structure on these guys. So the ordering is the obvious thing. If the edges are a subset of the edges of another graph, then those two are ordered with respect to each other. And unions are given in also the obvious way by taking unions of vertices and unions of edges. Okay, so again, some examples, since it's easier than reading this dense text. This graph is less than this one, just because there's less stuff around, basically, in the obvious way. And if we take the union, so we saw these guys earlier. We know that this guy is not a pure state, so it's a mixed state. We know that this guy is not a pure state, it's a mixed state, because it isn't a complete graph. We take the union of these two guys, which is kind of like mixing them together, forming a convex combination, and we get a pure state, which seems slightly wacky and possibly shakes slightly the intuition that we can think of CPM of thing in general as always been a thing where we can think of it as doing mixing, and I think there'll be remarks on that later in another talk. Okay, so I've got to my conclusion without being told to stop. Okay, so I think that the point here is this is actually a very simple visual way of thinking about REL, and it's complementary with the string diagram stuff. It tells you different things. I think that counting question I addressed at the start, you wouldn't really know where to start in string diagrams without kind of being told the answer. In terms of applications, see Stefano's talk in a minute or so's time. Oscar, who's around somewhere over here, has got rather a beautiful characterization of states in CP squared. REL by considering coloured graphs. So this perspective of thinking these things as graphs seems to be useful. And the reason you might be interested in this is because, as we mentioned earlier, for linguistics, there were at least two different reasons to think about mixing things together. So interested in iterating this construction is then motivated by that. And then we might think about repeated iteration of this CPM construction, and an MSc student this year is looking at that question, and she's got some axiomatization results in that direction, is also looking at some more concrete stuff. So there's work going on in that direction as well. That is be done. Thank you.
So we got time for a quick question, as they like to say. I think I'll give preference to people who aren't here all the time. So Jason?
Have you looked at when you're counting these things, did you look at the online encyclopedia integer sequences?
Yeah, that's what pointed me in the right direction. Was my little program got me far enough. When I tried CP squared REL, I blew up well before that was going to give me any hints, unfortunately. So yeah, it didn't give me a clue in that direction. But then fortunately I have more powerful technology, which is Oscar, that seems to sort out that instead.
Bob?
Since you point to the order and the sort of local enrichment structure, have you considered using like Carboni-Walters type axiomatization for REL and see how this actually refines to an axiomatization of CPM REL possibly?
I haven't looked at that, so.
Because you've got the order structure, you've got everything there.
Yeah.
So I think this should
Maybe an obvious sort of next thing.
Yeah.
Oh, that sounds like a great idea. Yes, Ross. Sorry.
So the Q states as a complete graph. Do you see anything interesting about the discrete graphs?
Not except that they're kind of completely mixed up things in some way, but I'm not very comfortable with using this word mixed, except it seems obvious. I'm not sure mixing is the right term at all. I think there's something to be said about what really the non-complete things are there. Is it really mixing or is it something else that's going on?
Okay, I'm afraid there's no way to manufacture extra time, so we have to move on. So thanks. So as soon as he figures out how to get out of the last talk slides, we'll have Stefano Gugioso giving us a